It's a privilege for me to be here today and introduce you somebody who all of you know probably as much as me, but let me try to do justice to somebody who probably touched our lives, touched the lives of most of us who are here. This was a cartoon in the fest which was brought out for him and sort of iconically used at many places. It basically looks at the various things which he has done, and of course, the tune which he always sang, the quasi-normal modes. Vishu is associated in the minds of most of us with quasi-normal modes or the ring down of a black hole. The prediction that his simple calculations made was dramatically verified after 46 years with the discovery of gravitational waves by LIGO. It was wonderful that he could experience exhilaration and satisfaction regarding his contribution when the whole world was cheering and applauding. The black hole man of India will be remembered for a long time for his seminal contributions to understanding black holes, for the word pictures and the Sidney Harris-like cartoons he created to share with his professional colleagues and lay public the esoteric consequences of Einstein's general theory of relativity. His talks inspired generations of students to a career in science, and via activities at the Jawaharlal Nehru Planetarium and the Bengaluru Association for Science Education, the inspiration lives on. A brief thing about his timeline: he was born on 6th March. He finished his BSc in the Mysore University, then the MSc at the Central College, which was affiliated with the Mysore University then. Then he went to Columbia University and then completed his PhD at Maryland with Professor Charles Misner on the topic, which is the stability of the Schwarzschild metric. After stints at the Institute of Space Studies, the Boston University, New York University, and the University of Pittsburgh, in 1976 he moved to RRI, where he was there till 1992. Then he moved to IIA, from where he retired in 2005. And from 1988 to almost towards his end, he was involved with the Jawaharlal Nehru Planetarium in various capacities. On January 16, 2017, he breathed his last, and is survived by his wife Saraswati, daughters Smita and Namita, and his 3 grandchildren. Let me begin with a brief history of black holes. As you know, relativity revolutionized our understanding of space and time. It united them into a flat 4-dimensional space-time in special relativity and made it curved and dynamic in the general theory of relativity to describe gravity. Gravity is no longer an external force, but synonymous with the geometry of space-time. And in 1915, Einstein arrived at the correct field equations, completing the quest he began in 1907 to obtain general relativity, which is his relativistic theory of gravitation. Mathematically, the equations were complicated, and so he was surprised that within a year, Schwarzschild discovered the exact solution to these equations, representing what we say is a spherically symmetric, asymptotically flat vacuum solution whose outer region is strictly static. The solution had an unusual feature that certain components of the metric vanished while another diverged at what was referred to as the Schwarzschild singularity, or better, the Schwarzschild surface. In 1939, Oppenheimer and Snyder showed that the person who rides through this surface on an imploding star will not feel infinite gravity or see any breakdown of physics there. However, these results were not taken seriously because of the mental connotation associated with the word singularity and due to the simplest dust model which they used in their treatment. So these objects for a lot of time was referred to as a frozen star in the Soviet Union and the collapsed star in the West. The realization that this was due to a choice of coordinates or a coordinate singularity was a long time coming and conclusively settled in 1958 by Finkelstein and later by Kruskal, who discovered a new reference frame for the Schwarzschild geometry. One of the important bizarre predictions of general relativity is the existence of black holes. It marks a one-way surface which can be crossed in one way but not the other. Things can fall in but nothing can come out. And in December 1967, in a lecture which is called Our Universe, the Known and the Unknown, John Wheeler first christened these objects as black holes. It's an idea which intrigues and fascinates scientists and the lay public even to this day. But the point is that general relativity is a complex and mathematical theory, often involves subtleties in its physical interpretation related to the choice of coordinates used in its formulation. So can one use a description of the Schwarzschild solution using more well-behaved coordinates? Even if mathematically a black hole solution exists, the possibility of it being a physical object in nature depends on whether it is stable. If a black hole is an object from which no information can escape, how can one look for it? Can one provide a mathematically elegant description of physical effects of a rotating black hole, like things like gyroscopic precession? And Vishu's seminal research centered on these topics, and this is what earned him the fond title of the Black Holy Man of India. Let me begin with one of the first papers, which almost is what we learn in our textbooks. So I consider one among Vishu's classics on this particular topic, a brief and elegant paper using killing vectors to provide a coordinate invariant distinction between the stationary Kerr and the static Schwarzschild black hole cases and the consequent existence of an ergosphere. This paper is called Generalization of the Schwarzschild Surface to Arbitrary Static and Stationary Metrics. And regarding this work, Bekenstein commented, I was familiar with the Vishu theorem that the infinite redshift surface of a static black hole is always the horizon. At that time, black hole physics was just getting started, and such neat relations between black hole features were rare. Vishu's theorem was a welcome hard fact in the middle of such folklore and helped clarify in mind what black holes were about. At the conference GR6, I had a long talk with him, and I vividly remember being impressed by the range of research problems he was going simultaneously. Just to go a little more technical, this is the Schwarzschild metric, and as Vishu mentions in his particular paper, for static sources and observers, R equal to 2m is an infinite redshift surface. It's also a null surface because it locally acts like a one-way membrane, and therefore, in that paper he asks this question. The question arises whether the two phenomena are interrelated or whether it is possible to characterize in an arbitrary metric surfaces exhibiting one or both of these properties. The question can be answered in the case of a static and stationary metrics. The time-like killing vector admitted by these metrics makes possible to analyze the problem in a complete coordinate independent manner. And then he basically adds, the infinite redshift results on a surface on which the killing vector becomes null. In an arbitrary static metric, it is also a null surface. That is, it is both an infinite redshift surface and a one-way membrane. Then he adds, the surface on which the time-like killing vector becomes null will itself be a null surface if and only if the rotation vector of the killing vector field also becomes null on it. Only under this condition will the infinite redshift surface act as the one-way membrane also. So basically, in this particular paper, he really made this distinction between the physical aspects of being a static limit, being an infinite redshift surface, and an event horizon. And this is basically what we today read in textbooks, that in the case of the Kerr solution, you have the infinite redshift surface, then you have the horizon inside, and there is a region between them, which is called as the ergosphere, because of which very interesting things sort of happen in the case of the Kerr black hole. The next important work is the work on the stability of the Schwarzschild solution. Vishu was the first to prove the stability of the non-rotating black holes under linear perturbations. And regarding this, Brandon Carter, who at that same time worked on similar problems, mentions Vishu was one of the first to appreciate the importance of this problem and who played an important role in persuading others to take the problem seriously as something of a potential astrophysical relevance by providing the first convincing proof that at least in one case, namely the Schwarzschild solution, such an equilibrium state can be stable. Elaborating further, Bernard Whiting wrote, Vishu's original discussion of stability showed that there was no superficial case establishing the instability, basically by dealing with single modes and by demonstrating the positivity of effective potentials. Establishing point-wise boundedness requires use of more refined tools, leading to a method that differs markedly in substance, but not at all in essence, from the relatively simple positive potential approach. Vishu made a number of significant breakthroughs. So this is the paper which Vishu wrote, and you will hear more about it in Amitabh's talk later. The last part, the classic paper which I want to talk about, is Vishu's work on quasi-normal modes. Vishu was the pioneer who explored how black holes respond when externally perturbed, and proved that regardless of the perturbation, Schwarzschild black holes get rid of any deformation imparted to them by radiating gravitational waves with a frequency and decay time that depended only on their mass. These characteristic waves are technically termed quasi-normal modes. After the announcement of the gravitational wave detection by LIGO, Vishu laid the claim to the nom de plume Quasimodo of black holes, as Rajesh mentioned. Quasi-normal modes are like the dying tones of a bell struck with a hammer and are referred to as the ring-down radiation. Vishu's work is fundamental to our understanding of black holes and began a new chapter on how to study them. Again, this is the classic paper, and you will hear more about this in the talk by Satyaprakash. But Vishu himself had a take on all this particular work, and he writes in the Vaidya Raichaudhuri lecture which he gave, Vishnu proposed the following problem for my PhD thesis. Take these two entities that are now called black holes, revolving around each other, they come closer as energy is radiated away in the form of gravitational waves, they coalesce into an ellipsoidal Schwarzschild surface, still rotating and radiating. Study the whole process, computing all the characteristics of the emitted radiation. Fine, I said, I will be done. At the time, I did not realize the magnitude of this problem. Had I pursued it, I might have entered the Guinness Book of Records as the oldest graduate student alive, that too without financial support. Anyway, this proposed problem required the understanding of two aspects of black holes, the geometrical structure of a black hole and the perturbations of its space-time. Then he goes on and then writes in another fest, it was the best of times, it was the worst of times, for me that is. That was in 1969. My original work on quasi-normal modes was terribly exciting to me, and that is the best of times part of the story. Now for the worst of times aspect, unfortunately, no one seemed to be interested in this kind of research. After all, neither black holes nor gravitational radiation had been detected, but only theoretically predicted. Why should anyone spend time investigating the interaction between two unobserved entities, perhaps of doubtful existence? He writes this in the Shooking Fest. I met Vishu in the Einstein Centenary Symposium at the Physical Research Laboratory in 1979. Though I have wonderful memories of this symposium, the most memorable ones was on Vishu's lecture, which was entitled Black Holes for Bedtime. It was really a magical experience because the talk was an exact cocktail of science, art, humor, and caricature. And for the first time, I realized that equations were not necessarily abstract and unspeakable and could well be translated in the best literary tradition. But of course, you had to be Vishu. And what you see in the poster for this particular meeting is really all the elements which appeared in that particular talk. So he takes basically Alice in Wonderland and really maps to black hole concepts various things which appear in this particular remarkable book. I will go and discuss Vishu's tenure at RRI and the kind of work he did there. From 1975 to 1980, in these initial years, he essentially worked on exact solutions, trajectories in the presence of electromagnetic fields, the use of the Hertz potential approach to study perturbations in spacetimes, and these were his collaborators during that particular epoch. This Chitre is D.M. Chitre, the brother of S.M. Chitre, who most of you know about. After 1980, I basically was at RRI, and then I worked very closely with Vishu. And Vishu and I basically explored problems of classical general relativity, but the point was that we tried to look for impact in astrophysical applications. The basic theme normally is, and this was basically Vishu's vision, that if you look at perturbations of black holes in general relativity, they carry signatures of the effective potentials around them, and one could look for them by examining things like how neutrinos behave if there is gravitational collapse. Do objects like ultra-compact objects, which I will explain in a little while, do they exist if you believe in general theory of relativity? And then you ask questions like, can you discern possible differences between black hole solutions in general relativity and other theories of gravity by looking at quasi-normal modes and the properties of their horizons? Can you use standard things like Frenet-Serre methods to study effects like gyroscopic precession? Can you characterize black holes in higher dimension in a covariant and geometric manner by extending his original work on coordinate invariant characterization of black holes. And then astrophysical issues like how does the presence of a magnetic field affect the effective potential around a black hole, and hence how does it affect accretion around black holes. Mathematical issues really studied, really depended on what are the properties of different spin perturbations, and can you separate them in arbitrary spacetimes in general theory of relativity. So I'll just take two important topics which I think were sort of interesting. So the basic point is about the existence of what we call as ultra-compact objects. If you believe, if you ask, what effects, how are the general relativity effects determined in the case of bodies, they're basically determined by the ratio of the radius to mass. For example, if this ratio is greater than 6, the body is almost Newtonian. For black holes, this ratio would be 2. If you take a static fluid star in general relativity, Bagdal showed, for example, this ratio would be something like 2.25. So the question is, between this 2.25 and 2, between this 6 and this 2, there is a small region. And the question which we want to ask is, if you look at neutron stars, can you have bodies where this ratio is less than 3? Why do you want to focus on that value 3? Because for ultra-compact objects, the general relativistic effects are stronger and could be different, since the exterior Schwarzschild potential has a barrier at r equal to 3m. If you look at the electromagnetic perturbations, for neutrinos approximately it's around 3m, and therefore some modes of emission, they would be sort of trapped by bodies of this particular kind. And then to really investigate this particular question, we used what is called as the core envelope models for neutron stars, where you basically deal with the uncertainty in the equation of state of neutron matter by only using the equations of state up to a certain value of density, and beyond that using only general properties like the positivity of the energy of rho, the microscopic stability of the model, and so on. So these core envelope models, if you use for neutron stars, we found that these models do allow for such compact objects. But the point was that if you actually use the available neutron star equations of state, you really don't lead to such particular objects. So the other question which Vishu was always fascinated about was, though theoretically neutron star masses can go up to 3 solar masses, all the observed masses used to lie somewhere between 1.4 or 1.6 solar masses. So Vishu's idea was, is it smaller than 3 solar masses because of stability considerations? So what we basically showed was that by using these core envelope models, stability criteria do not bring down the mass limit. So this was one interesting work which I did with Vishu, and I think this was quite interesting. And again, this is the reference to that particular work. The other interesting work which we did was work related to studying the general properties of black holes in higher dimensions by using some standard things which you learn in elementary differential geometry, which is the Fresnel formalism, but extending it to 5 and 6 dimensions by studying killing trajectories in these particular spacetimes. So what you basically use is the fact that when you look at the Fresnel curvature invariants like the kappa and the tau 1 and tau 2, they, for the killing congruence, they can be related to the effective field strength, which you can define in terms of the killing vectors themselves. So then what you basically have to do is investigate, if you want to generalize Vishu's results in 4 dimensions to these higher dimensions, you basically have to look at algebraic relations which these FAB will sort of satisfy. You use some standard techniques from matrix methods, and then you can basically try to find relationship between these Fresnel invariants by using this method. And then you can really generalize the same property that if you define the rotation tensor in higher dimensions, you can show exactly the same kind of result which you had, that the surface on which the time-like killing vector becomes null is a null surface only if rotation is sort of null. So this was a very interesting result. The proof came in a different way, but the fact that such a result exists was really interesting. We also sort of worked with scalar perturbations of black holes in other theories of gravity. For example, at that particular time, there was a black hole solutions in quadratic, in a theory which had quadratic Gauss-Bonnet corrections. This is called the Bowler-Desert solution. So basically, we studied the scalar waves in this particular background and tried to investigate the quasi-normal modes of this particular black hole by WKB methods. Then when Vishu moved to IIA, he continued this work on Freyne-Serre formalism to study the analogues of inertial forces. This is the talk by Rajesh Nayak in this particular meeting after the lunch. He also worked with another student, Ramchandra, on the role of Killing tensor in the separability of wave equations. And also, he was interested in this particular question that if you are talking about a black hole solution, not in a flat background, but in a cosmological background, what are the differences in their sort of properties? So this essentially summarizes Vishu's work in all. But the important point is that in 2012, with a sort of visiting student, Surej Hegde, he was still interested in different aspects of black holes. So this is the last thing you will find on GRQC. It was basically a paper preprint which is called Analytical Theory of Optical Black Hole Analogues. You can see Vishu's love all over again. And the last line, these optical black holes can be employed to investigate black hole phenomena in the tabletop experiments. So essentially, I have gone through all these properties. So if you look for the different areas, and if you really ask what is the joint theme, Vishu always sort of believed that even though black holes are classical objects, you can think about them in terms of the techniques you use in quantum mechanics, scattering methods, the effective potential around them, and so on. And you would find that all this research essentially links around that particular set of ideas. How was it working with Vishu? If you look at Vishu's collaborators, there are about 30 of them. He had 3 students, Biplab Bhaval, who works for Google these days, Rajesh Nayak, who's here today, and B.S. Ramchandra, who's also in Bangalore today. He had 3 formal postdocs, Sanjeev Dhurandhar, myself, and then later on Sai Iyer. And personally, if you talk to most of them, they would basically, all of them would agree that it was really a pleasure working with Vishu, because there was never any pressure, there was no generation gap, there was always a natural possibility to grow and contribute your best. There was an easy personal rapport, a refreshing sense of humor, an unassuming erudition, and most importantly, a warm and wonderful human being. Through Vishu, I met in RRI the who's who in general relativity when they visited Vishu, people like Brandon Carter, Malcolm McCallum, Brill, Hartle, Chandrasekhar, Penrose, Isaacson. And I recall that Vishu held in high esteem some of them, Charles Misner, of course, Engelbert Schuking, Richard Isaacson, George Ellis, Papa Petru, Cohen, Ehlers, and so on, and really had a wonderful relationship with many of them. I really enjoyed co-editing with Vishu many volumes, especially Highlights in Gravitation and Cosmology, Gravitation, Gauge Theories and the Early Universe with Professor Mukunda also as one of the editors, and another volume which is Geometry, Fields and Cosmology, Techniques and Applications. Together with Ratnakar, who was the librarian at RRI, Vishu was instrumental in setting up in RRI a film club in the 1980s to really get access to movie classics from the film archives at Pune and from the consulates of the French and German, with whom we had a lot of relationship at that particular time. Vishu really was involved after he returned to India in building the GR community and taking it to the next level. Together with Jayant, he played a key role in bringing the long due recognition to the doyens of general relativity, which is P.C. Vaidya and A.K. Raichaudhuri. A volume entitled Random Walk in Relativity and Cosmology was co-edited by them. It was released in 1986 at RRI, and the royalty from its sales, supplemented by royalties of the ICGC proceedings, were used to set up what we today have as the Vaidya Raichaudhuri Endowment Lecture of the IAGRG. He was also involved in a group which initiated, planned, and organized UGC schools on general relativity and cosmology in the 1980s. The motivation was to extend Indian research, which tend to be more on mathematical aspects of exact solutions, to modern research frontiers in cosmology, early universe, and relativistic astrophysics. This led to the ICGC meetings, which are organized every 4 years, because it was recognized that due to limited resources, participation of the Indian researchers in these international meetings was very, very limited. So the idea was to create an opportunity for the Indian relativists to interact with international experts on the frontline research areas in relativity and cosmology, so that they could move to the next level their research and make it sort of more relevant to what was happening in the international community. But these meetings also brought out the cartoonist in Vishu during the first international conference on gravitation and cosmology in Goa. What used to happen was, in between sessions, cartoons would appear on the screen anonymously, and by the end of the meeting, there were multiple reprint requests for those cartoons. Cambridge University Press, which is a very staid publisher, was really happy to include these cartoons in these proceedings, and Vishu's cartoons in the ICGC proceedings really became a treat to look forward to. He really made a series of cartoons on gravitational waves in these proceedings. They really deserve special mention, as I will show you, but they remain incomplete because I don't think he made one after the discovery. So this was the Goa one. This is the gravity wave detective, who basically says that I think it exists, therefore I am. When he went to the meeting in Ahmedabad, he basically had a more complicated one, because by that time LIGO and etc. people talked about chirps. So Vishu had groans. If you can look for each one of them, you can see there's no data, but there's a lot of analysis. And then the gravity wave detective now says, I think, therefore I think I am, therefore it exists. And finally, much later in Cochin, he had another one where the detective essentially now becoming existential, and then he says, I think it exists, therefore I am. I think I am, therefore it exists. It exists, therefore I think. What if it doesn't exist, therefore I am not? So you can see Vishu could really take the theme sort of forward and forward, and that was, I thought, very, very special about him. And it's interesting that he not just influenced people close by, people get influenced even much later. Just on the day he passed away, Niels Anderson wrote to Vishu an email which said, I have recently done something that I think might amuse you. I have written a little book involving Einstein, relativity, and a fair bit of fictional freedom. Now I think it is fair to say that my attitude to this project has been heavily inspired by your storytelling, your drawings in the bathtub book. And this is a book which is just sort of coming out. If you are interested, you can order it in Amazon. Vishu's public lectures inspired a number of students all over the country. His lectures at the Bengaluru Science Forum, started by his guru Narasimhaiah, always drew huge numbers. He was always a bestseller in these events. He never disappointed the audience. Without diluting the profound ideas he would discuss, he would lace these talks with subtle humor that came seamlessly. At Vishu's passing, countless echoed what Satyaprakash, who is going to give one of those talks, who wrote to me, this is devastating. I have lost a teacher, a mentor, and a friend. More than anything else, we are going to miss his serious sense of humor in all walks of life, especially science. Vishu also had a part of, was always worried about the social impact of the science we are basically doing. And in those years, together with a committed group, which involved people like Sanjay Biswas, Margaret Biswas, and many others, he was involved in bringing out what is called the Bulletin of Sciences from 1983 to 1993, to set up a forum to seriously discuss the social impact of science and technology. And when Chandrasekhar visited, Vishu had talked to him about this, and he was very much impressed about this particular activity which Vishu was involved in. To find means of sustaining such activities, he the main problem was how to keep such activities going. So he co-edited with Sanjay Biswas and D.C. Malik a very interesting volume, which was called Cosmic Perspectives. And this volume, the royalties of this was really used to look at this particular, to fund this particular activity, but eventually, it had to sort of fold up. Finally, the Jawaharlal Planetarium itself, it's a wonderful testament to Vishu's vision, which showcases his multifaceted personality in science communication and education. He started as its founding director in 1988. He brought together a dedicated and talented team and inspired them to build a world-class planetarium, scripting unique shows, integrating the best in science and astronomy. But this is the special thing. with the best in world and Indian history, art, literature, and music. By example, he set high standards for all the JNP personnel and mentored them till the very end. But JNP was not to be just a theater. It had to play a role in science education in the city. And therefore, in 1992, he set up the Bangalore Association for Science Education, because by using this, Vishu wanted to systematically expose, attract, and mentor students from school, high school, and colleges for an eventual career in science. It's no wonder that more than 100 students who passed through Jawaharlal Nehru Planetarium are either pursuing PhD programs or completed it, and some of them already are faculty at many institutions, and you'll hear more about it in the talks by Shaileja and Vijay in the afternoon. I'll end by the two bubble bath books which Vishu wrote. One is Einstein's Enigma of black holes in my black bath, in my bubble bath. Just look at the contents of this. This is really a book on relativistic astrophysics, but look at the content. And then another one about cosmology, again, universe unveiled, the cosmos in my black bath, in my bubble bath. And again, you will see, if you look at the contents of this particular chapter, it's really teaching you very serious cosmology, but going through the historical development of this particular subjects, but in a fashion which was uniquely Vishu. So let me conclude. When the gravitational wave discovery by LIGO was announced last year, Vishu was elated. We have never seen him so high, thrilled by the possibility that soon there would be events where the quasi-normal modes would be even more strong. It was really touching because later on Vishu was at the hospital, but anytime we went to the hospital to see him, he would be so excited to express his excitement about what was happening and his own encouragement to take these activities sort of forward. The profoundness of this discovery is in the realization that the black hole, which is purely a geometric object without any hard surface boundary, rings under perturbations like a material object. It is indeed the most telling and visible defining property of a black hole, and Vishu was its discoverer. By all accounts, it's a discovery that will go down in textbooks. If that be the benchmark, there are only few other contributions from India, like the Raychaudhuri equation and Vaidya's radiating star, that will make this particular grade. On the other hand, this discovery sits alongside the celebrated result of black hole's nowhere theorem. Most important of all, it is one of the few predictions that have been brilliantly verified by the observation of gravitational waves produced by the merger of two black holes. The observed profile has uncanny resemblance with what Vishu had predicted long back in 1970. There are very few predictions which are actually verified by experiment and observations. Vishu's black hole ring down is one such. This is the true and ultimate measure of an insight which is seminal. So many aspects of black hole research which Vishu initiated have really sort of emerged over the last 50 years. And in a first volume, which was edited by Biplab and me, you would find many details of this in this particular volume, which is freely available for download for anybody who's interested. So let me end by quoting a stanza which Vishu always sort of quoted. We will miss Vishu, we will miss you, Vishu, but we will always try to remember what you say, that traveler, there is no path. Paths are really made by walking. Thank you for your attention. Sorry, I overshot probably, I didn't.
No, you did not.
I did not? Okay. Thanks.
Can I ask a technical question? So when you...
You're the technical speaker, so I'll try to answer it.
So when you say the rotation, you mean the FAB is null. So in the talk you said that...
So the ZA, so the killing congruence, you know, if you try to work out the relationship between the norm of the vector and the killing vector, it's the rotation of the killing congruence itself. Right?
That is...
Yeah. So in general, you know, there is a part which is related to the nullity and another part related to the rotation. In the static case, because the killing vector is hyperspace, is a normal congruence, that term is not there, and therefore the null surface and the infinite redshift surface become the same. In the Kerr case, that extra term makes sure that, you know, because of that, whatever is the infinite redshift surface is not a null surface, and the null surface is something different.
Yes, Rajesh.
That he was using many things inspired from quantum mechanics and so on, but he didn't really work on the quantum effects.
That's right.
So what did he think of, say, all the Hawking results and things which did have some quantum mechanical things, or more generally about quantum effects?
So, the point was, at that particular time, my PhD was on Hawking radiation from Kerr black holes. So, I moved in as a postdoc with Vishu, basically because his basic point was that was sort of the most interesting thing happening about black holes. And then, since RRI was basically an astrophysics institute, the idea was to see the impact of GR on astrophysical problems. So that is the reason the idea was, whether these things would have astrophysical consequence. But Hawking radiation itself, direct, because of the fact that they are important for mini black holes. Therefore, astrophysical black holes, they are not important. Slowly, we went away from it. So I decoupled from doing quantum field theory in curved space to doing classical GR because of my interaction with Vishu for the 10, 12 years when we were working together. But he was, of course, the fact that, his whole thing was, when I said quantum mechanical, his basically point was, how did we know about the proton, right, by scattering experiments. So his point was that maybe the best way to think about to look for a black hole is by really looking for scattering. So, and then, for example, for calculating the quasi-normal modes, right? Typically, you cannot really calculate it analytically. But we know that in quantum mechanics, there are these Eckart potentials or potential where you can solve things exactly. So, for example, one of the problems he was trying to use was, can we try to numerically use the Eckart, one of the papers which he has, is can we use the Eckart potential to really model, black hole, quasi-normal modes and so on. So, you would sort of think like that, but he was never actually interested in working on the quantum aspects.
Sir, despite these...
That's a non-scientific question, I'm not interested in that.
I have a last little question. So you mentioned about these theories of gravity in which you add on the Gauss-Bonnet term. So there must be a calculation of those frequencies.
Right.
So is there a limit in which they actually just go over to the Einstein?
Yeah. So, in the model which we had, what really happens is that, but the point is that Einstein's GR is modified with a Gauss-Bonnet term, but that coefficient, we had sort of chosen as an arbitrary parameter. So essentially, we could say the effect of it was in terms of the particular. If that parameter is so much, then the quasi-normal mode is shifted to this particular value. That's how that particular works.
Thank you, Bala. And let's give Bala